so this sample we have loaded now is cross sections made by the broad ion beam miller of paper that has been coated with graphite on one side. I mean, these are old samples where we studied those kind of coatings. And what we want to discuss in this case is the detector positions and what shall I say, how to use the detectors. So let's start up. All right. You want to focus here. You see that is the copper tape. Mm-hmm. You see here. That is the highest point. It's nice to start with that. So you focus on that and you can raise up the stage up to 10. And we want to come to 10 millimeter. And then we put in we can start by going to 10 millimeters. Okay. Is it in focus, or?
As good as I can make it.
Yeah. And you raise the stage. And pull it up to 17 or something like that. Yeah. And as always, we follow the safe protocol. We go half the distance we want to reach and check the focus again to recalibrate the stage control. And then we just continue iterating that. Yeah, so you can go to 10. So this is mainly low magnification work. So we change the view field to like 1 millimeter. That I guess is nice. And then we find one of the cross sections. So if you move out towards the paper, exactly there, right? So you can do auto contrast also. Change beam intensity to like 16 also. So we get like good signal. We talked about this earlier. If it is low magnification work, sample is properly coated, it should survive high current. Mm-hmm. And then that simplifies the session by the noise level goes down and you can scan much faster and so on. Just continue to translate across south, so to say. And then you will start to find the actual cut there. This side.
Yeah, sorry.
Continue downwards. More. There you see. Here you see it becomes very. You can actually try to make it larger, so the users can easier follow along what we're doing here. So here we can see this is the roughness we have on top here. Mm-hmm. That part. That is how it looks like when you cut something with a razor blade. Mm-hmm. So in the microscopy world, that's become very rough, mm-hmm. and fiber sort of bends and breaks and so on. But then more to the south there is the cross cut after the miller. So that's what we see here. Mm-hmm. This section. And what we are having here is that this dark gray part is the cross cut of the paper, and this is the top surface of the paper. So we have a little bit perspective view here. Mm-hmm. And then this area, that is just the void. What shall I say? The paper is a little bit tilted, so we cannot see the back side of the paper. We only see the top part and the cross section. Mm-hmm. And this area is, what shall I say, the substrate, the stub piece. Mm-hmm. That's why it's out of focus. But if one wants to analyze something like this, if we want to sort of save an image, it's what we would like to align the sample, right? It would be so much nicer. Let's say I take, we talked earlier that we can rotate the scan direction instead of rotating the sample. So if you rotate it there, then you can align it, right? So make it horizontal. No, you scroll left like that.
Like that. Okay.
So now we start to understand what we're looking on. So this is the cross section. This dark stripe is the coating, and here we see the coating from top, this on the surface of it, and all these graphite flakes. So if one wants to, the first thing that comes on mind, okay, one wants to align it as you did, right? And there's two ways of aligning it. One is to rotate the scan as you did, but we can also rotate the whole stage.
I see.
And what shall I do? Which one is better? I mean, earlier we talked about rotating the beam or translating the beam doesn't cause vibration in the stages. So for high resolution work, that can be beneficial. But this is low resolution work. So here we're free to choose. And rotating the beam is, of course, convenient. But the perspective where the light comes from in the secondary electron image is where the position of the detector is. Right? So the chamber secondary electron detector is up here. So it casts light in a low angle. It's a little bit of shadow casting sunset effect here.
Yeah.
And we can take advantage of that to emphasize the contrast. So we want the light to come to the front, the top surface of the paper. Then we will easier see what's supposed to be the surface and what's supposed to be the cross section.
Yeah.
So if we look on how it actually is rotated, we can try different rotations. So if it says keep view field here, then I can rotate the stage and it will remain, the thing we're looking on will be kept in view field, right? Because the stage only rotates around its mechanical central axis. So if the sample is positioned, now we have the sample in position 7, which is very close to the center. But if it's in the position 4, then of course it will go away from view field. But if you have that thing clicked, keep view field, then it will, it's a computerized stage, then it will calculate the motion and make several dimensional motions to keep the sample in view. So that's handy. And now it says that it's on 30 degrees rotation, and we can change this to another value. And so if I write 0 here, it then becomes 0. But what I can also do, I can give a relative coordinate. So if I choose double minus, that means, and I write 90 degrees, that means I want to go counterclockwise 90 degrees, not to the 90 degree position, but go another 90 degrees. So you can also do double plus sign.
I see.
So let's say we rotate it 90 degrees. You see it goes out of view and then it will come back.
Yeah.
Now I have rotated it. And look on the surface now. You see it became much brighter.
Yeah.
And it's a little bit hard to see on the camera view here. But now that paper that is in that, there's two samples here, but one of the papers is now facing the detector, right? It's facing this detector.
Yeah.
So that means the top surface of the paper will be illuminated by the sun from the detector there, right? So then we get a very nice contrast change between the cross section and the surface. So now we still want our paper to be horizontal in the image, right?
Yeah.
But that we can fix with the rotation of the beam. So if you rotate it back now, yeah, like that, right? So now we have optimized the contrast by taking into account the position of the detector. So since this is a very, shall I say, long and flat sample, in this particular case it can actually be beneficial to change the scan ratio. So we can make something like this. Now, we don't have to scan a whole image and just scan in empty space, right? So, and if we go in here and look, you see we can do some correction here. You see there is a lot of stigmatism, right?
Yeah.
And also some column centering needed. So you can try to fix that if you want. Stigmatism also. You can try to focus first. See there, find the midpoint where the lines sort of become round instead of lineish. Yeah, that's great. That's great. Now you do the trackball. Make the image sharp. Here it comes. Try left and right now.
There we go.
Great. Look, there you have it. All right. And we can go back to view field 1000 millimeters.
Wow.
So now I have a very nice image there, right? And we can do our scan here perhaps also. So the idea is, I mean, we want to emphasize the contrast by taking advantage of the detector position. So it works in favor of creating the contrast for us. Now we have a very nice image where we very easily can see it is aligned, the detector is in the right position, and we use the beam rotation to bring it horizontal, so the visual interpretation will be easy, right? I mean, here we see the graphite, and this is the paper, and all this is the cross section. So the graphite forms some, what shall I say, plates. So we see the plates around here. And then also, one can talk more about the detectors. I mean, this is the SC detector that we're using now. And if we click on here, we can find something called here, scintillator grid SC. So this is the voltage on the secondary electron detector has two voltages. One is the scintillator part, and one is the, what shall I say, the attractive. If we zoom out here, that mesh has 270 volts applied to it. Positive. That means it will attract electrons. And these low energy electrons is more like a gas. So they are. So this is like almost like a vacuum cleaner. It sort of sucks the electron up there. And how much it's sort of the sucking power of that detector is decided by that voltage. And we can change that. And we can look on the details in our image and see what's going on. Like that. So let's see what happens if we drop it. 0. Perhaps we should make a comparison image so we can compare. We go back to this one first, and we make this one small, and let's scan it. And now we drop to 0. And we can do new auto contrast. Scan it. I think you're supposed to be able to go to negative also. Let's see. I don't know how much you can go on this one. Is it just 0? Sometimes you can have negative. This machine cannot do negative.
Okay.
All right. Let's see if we can have higher values. Can we have 400? What we can have?
That works.
A little bad we couldn't have negative there, and that would have been nice. So let's see if we see something here. Some differences. So now we have 0, 270 and 400 volt on the top one there.
Mm-hmm.
How do you fit everything on screen? I must say they actually look pretty much the same on this sample.
Yeah.
A little bit disappointed about that.
What were you expecting?
What we are expecting is that attraction level of the detector makes, what shall I say, the electrons, what shall I say, it becomes easier for the electrons, the higher voltage we have.
Mm-hmm.
So that means electrons that goes in the wrong direction. I mean, the secondary electrons, they scattered in all directions.
Yeah.
So the ones that goes to the right, away from the detector, if we don't have any, what shall I say, electric field on that mesh, those electrons will never turn around and go back, so to say. So that means if we look on things that facing now the detector, and then we have, like here in the image, you see these holes.
Yeah.
Some of these holes have electrons going in the wrong direction, so to say, right?
Mm-hmm.
The things that are in the shadow will be affected by that voltage. So the higher voltage, the less shadows we will have in the image.
Yeah.
So if you look on this image with the 0 voltage and this one with 400 voltage, but I will say on this particular sample, the porosity is not so much, so we actually see that. I think it looks very similar, all of them.
I agree.
Do we see anything on the actual cross section? Oh, but here I think we start to see. So this is another 0 volt. So now we have 0 volt on the top one and 400 volt on the lower one. And if we look in this hole here inside the paper, you see the thing that's in the bottom there. With 400 volt, electrons coming out from that are able to go to the detector. But those ones, you see, they are almost gone now.
Yeah.
So there you can see a contrast change. So electrons that is going away from the detector are not able to turn around because there is no electric field pulling them back to change the direction. But these guys have that 400 volt, it helps them. Yeah, that's a nice detail. I can set that to 270, and then we shall. We are on 10 millimeter now, working distance, so it should be safe to push in the RBSE detector. We want to go up closer to the detector, 8. But then we switch to the backscatter detector now. We can directly see, what shall I say, some new phenomena. We can see that, you remember yesterday I said that in literature, they say that the backscatter detector's contrast is mainly elemental composition. And then I said that topography is also actually a part when it comes to that kind of macroscopic topography.
Yeah.
And here we can see a nice thing because we see the crosscut here that is flat facing directly towards the detector, it becomes very bright in contrast.
Yeah.
Compared to this surface on top here, that is like 90 degrees away.
Yeah.
So the scattering of the electrons depends on the angle of the surface, of course.
Yeah.
So we see, and in this case, it is actually beneficial because for us it becomes very easy to, what shall I say, study the cross section. But what we want to see now, if we want to zoom in now a little bit closer here and look on these pores here. You can make 200 perhaps, or 250 when we get the whole paper. We scan this. So this is a zoomed in part of the cross section. And then there is this case that there's many times you want to use computer software to calculate how much pores you have and so on. And then those algorithms, you see this area. That, I mean, this whole thing will be sort of the pore area, right?
Yeah.
So the whole thing here will be the pore area. And that is the fiber that's inside the pore coming out here.
Yeah.
So, but the algorithm tends to misinterpret these things. So we want to sort of, can we improve the imaging conditions here? So the thing that is, we don't want to see the stuff in the holes, basically, and just see the surface. And there is a nice way of doing that, because if we look on the backscatter detector, it's here now. And it picks up the signal here. But we don't have to have the detector. It's a movable detector. We can change the position of it. So I can move the detector out. So if I look here, here is the original image. So if I zoom out, here is the hole that was looking through the detector. We can pull out this. And we pull it all the way out. Just remove it, the whole detector. And then we have the paper left. Here. You can go back to your view field 250. Of course, since the detector moves away, we are losing signal because most of the electrons scatter straight up.
Yeah.
But those that scatter to the right and still reaches the detector, you see, right?
Yeah.
Now we have fix the contrast here also. Now we have an image that doesn't show those kind of features inside the pores. You see, now all the pores is all black.
Yeah.
So we have very good contrast. Very nice to push to computer software afterwards. You can put them here side by side. Let's see, now they are the same size there. So here we see stuff inside the pores, and here it's completely removed because we just moved the detector into a new position. So that is the part of what did I talk about there now? We have talked about BSD detector and no, the crosscut, that part we have done. Those we have done.
Only 5 more to go.
These ones we have done.